Some more equivalence relations. So I'll get back to this theorem. I want to just have more examples. I just can't help it. We have so many good examples of equivalence relations. I actually brought this as an illustration of an equivalence relation that we have talked about. So starting with the, say, how about mod 7 equivalence relation? Okay, so there is a 0. I mean, there is no number 0, but this is 0. Okay, and then so what I do is I associate 1 with 7 according to our congruency. The 7 and 0 are equivalent, so I can put them together like this. Okay, and then naturally the next one will be 14. I make a full circle, and now as you can see here, 0, 7, 14 are combined together. Okay, and then I could keep going that way as many times as I need. So the next one is 21, and then the question is, so we're talking once again the congruency mod 7. Well, where are the equivalence classes in this representation? Yeah, well, I mean, yeah, we know what the numbers is. I just wonder if you see it right here. Where is it?
Where is what?
Where are the equivalence classes in this representation?
What he said wasn't right.
It was right, but it was algebra. I wonder if you see it right here, not on the piece of paper, which is okay, I suppose, but visualization helps a lot. Whenever we have some, we should try to use it. So,
Where they overlap.
what?
Where they overlap.
Where they overlap, right? In other words, I have between my fingers one equivalence class right here between my fingers. Okay? Another one, I could move from 29. Well, it's supposed to be 28. So 28 is combined with 21, 14, 7, and 0. I could put my fingers from 27 to 26 right here. So that's another equivalence class. And then for each number here, there will be an equivalence class there. Okay, so they are aligned within that spiral in a radial direction. So it will be going like this: 0, 7, 14, 21, and 28, and so on. And then I hold them by between my fingers. So that's the congruency. I want to take one step forward from the congruency idea. And have more and extend it to real numbers, right? Think about it. There are integers right here in the big letters, but there are a bunch of values in between. Okay, so as I do this thing, I also align numbers in between. For example, 27.5 will be aligned with 14.5, with 7.5, with half. Right. So in other words, the equivalence relation visualized by this is in fact an equivalence relation on real numbers. On real numbers. So as long as, well, what is that? How do I express it? The difference between two numbers is 7 exactly. They're equivalent. So like I said, 1/2, 7.5, 14.5, and so on. All of them are equivalent. Or a difference is a multiple of 7 rather. Then they are equivalent, and then it is better as far as visualization goes, because this is if it is just an integer, you have to imagine that there are no values in between. But if you speak of real numbers, they really have all the value, every single value here, every single mark on this thing. Corresponds to a real number, and vice versa. Okay, so then literally we take the real line and we roll it into a circle. Okay, so that is an equivalence relation, the point of which is a big deal. So it's the one that we talked about is 306 degrees that you start with being the an equivalence relation, but also it expands to equivalence relation on rotations between 0 and pi, right? So you can rotate beyond 2 pi, but you cancel 2 pi every time because you come back, and so there is no point of representing it with two different numbers. 2 pi is 0. Okay, so every trig function is 2 pi is same as 0, and that is how we understand rotations. Not angles as much, but rotations definitely. So once again, pass to pi, you have they start repeat themselves, and that's the equivalence relations. Okay, so there will be more examples of equivalence relations. Let's take another look at the theorem, which we almost finished, but I don't want to leave it as is, and do a little bit of let's write up the proof a slightly more accurate, careful way. So it's that way I would call what we have at the end analysis, just like I did it last time, and then rewrite that part that is feels kind of informal, and make it more precise. So once again, I call this analysis, not a part of the proof. Okay, so the idea of the proof is still here, and so we could use that analysis to write up the proof in a more careful way. So okay, so let's go with this again. That's a big idea about equivalence relations, is that not only they produce partitions, but they also are produced by partitions. Equivalence relations and partitions are the same thing. That's the idea. Okay, so then the idea is, if we have a partition just like that picture at the top, and then we declare that that's the definition. Where's the definition? Where's the definition? Okay, no, that's fine. So the converse, that is theorem, converse of our theorem, any partition of a set X is a collection of all equivalence classes of a certain equivalence relation on X. Okay, so we don't want to point out, we actually do point out what it is, and it is has an independent value right here. So sometimes part of the proof is actually might be better off. You might be better off if you have it outside mentioned, so that it is actually so important part of the proof. But let's just do the proof. So the idea of how to come up with that equivalence relation is this. So just declare that 2 points are within the same set of our partition. They are equivalent. That's it. So once again, remember, we're going backwards. We're going from partition to equivalence relations. Previously we went from equivalence relations to partitions. Okay, so that is the definition of the equivalence relation. Well, we got to demonstrate that it is an equivalence relation. So it is, as you can see, these are the 3 axioms. Reflexivity axiom is easy, because if X belongs to some X sub k, then X belongs to X sub k. So there is nothing to worry about. Symmetry axiom is obvious once again. And then the third one takes some work. So instead of going straight to the proof, I wrote it up. So that is the what I have here. This is simply the statement of the transitivity axiom to be proven. Okay, so how do I prove it? I rewrite it. I rewrite the 3 equivalences xy, yz, and xz as from our definition. So I take that blue box and repeat it 3 times for these 3 equivalences. Okay, so xy belongs to some xk, yz belongs to some xm, xz belongs to some xp. So without thinking about ahead just yet, this is simply rewriting. So that way we can put the equivalence relation idea out of our minds and concentrate on what we have. So we have 2 statements produce, supposed to imply this 3rd statement. Okay? So now the analysis right there in the box, not part of the proof once again. So at this time what I do is I observe that y is actually a common element of x sub k and x sub m. So let's write it up. Observe that y belongs to x sub k and y belongs to x sub m. I could even Well, you can see that in these two statements over there, this is what we says. In particular, we say that y belongs to xk, and in the second one we say y belongs to xm. Okay, so xk. One step at a time. I'll say simply, by definition of intersection, y belongs to the intersection, which makes it non-empty. So xk and xmm aren't disjoint. Therefore, they coincide by definition of partition. So partition, either they intersect or they coincide. It's either the same set or entirely unrelated sets. Okay, so once again, that picture at the top tells you the story. So they cannot overlap. So you cannot have y belong to both x2 and x3. There is no such thing. Okay, so if we just demonstrate it based on our assumption, the assumption on the left of our proof, of our statement of the transitivity axiom, we have demonstrated that there is an element there, that's y, and then which means that it is the same. So xk is equal to xm, or even you can say k is equal to m. Okay, so it's the same set. So it is named the same way as well. Xk is equal to m, k is equal to m. Okay, and then what do? We look at so rewrite once again. Rewrite our assumptions. This one, these two, we rewrite them. And so what we have here is xy belong to x sub k, and yz belong to x sub k, because it's the same thing. Xm is equal to xk. Okay? So, well, all right. So why does it imply that xz belongs to some p? No, this is how we do it. Slightly different. How should I? Well, let. We choose, it's our choice of p, so let p is equal to k is equal to m. Then what our statement turns into is this: xz belong to x sub k. Okay, so which is true. Okay, so let's examine the last part of the proof. So we demonstrated that x and m are the same, and then so that there is some index k or m that is available. So can we find that p? Okay, so that is the part of the I'm not sure if it is the entire, I mentioned that, or is it clear that for some k, for some m, for some p, what does it stand for in logical terms? For some. It's kind of informal language you may have seen elsewhere, but we're trying to use most of the time be very careful logically. So what does it stand for? For some? There is, yeah, that's right. So there is a k here, and here there is an m, and then there is a p. So from the existence of certain k and certain m, we have to demonstrate that there is some p. Okay, and then we did, because we, to begin with, they demonstrated that k and m are the same, have to be the same, and then we'll just declare, how do we find p? Well, let's just declare it to be equal to k and m. That's what I did. So, and then it then turns out that the statement that we're trying to prove, rewritten with this choice of p, is in fact true. You can see it, right? Everything is happening within the same set. So not only we demonstrated, we knew that x and y are in xk, but also yz also in xk, which means that, well, you know, xz is in xk. There's only one set of our partition to worry about, and it turns out that's all we needed. So that's the proof. Okay. So, okay, so then any partition will produce an equivalence relation. So it doesn't have to be some subtle or profound idea that where equivalence relation comes from. Take a set, cut it in an arbitrary way, and you have an equivalence relation. So, I don't know, you have a circle, you can have many relations between them, but how about I split it like this? I think, I don't know, a jigsaw puzzle. So I cut it in these many pieces, and then arbitrarily, and this creates an equivalence relation. If they lie in the same subset, then they're declared to be equivalent, and we have equivalence relation. Okay. The point of equivalence relation as a tool for studying things is that usually they are more subtle. So not like this. This is very unsubtle, as well as this picture is illustrating a partition is very unsubtle. Wherever every time example we took, the equivalence sets were interlaced, like once again, even and odd, like this. These are even, one equivalence class, odd another, but they are within integers they interlaced. Okay, so that is where really the challenge comes from, and but otherwise you can well, I actually have another one for another measuring device. Okay, so as you can see, same idea of measuring lengths, but look at it how it is folded. Not in a circle as I did with this one, right? But it goes back and forth. So not rotationally, but it goes back and forth. But I still could say the same idea. So I have my real line. So imagine this once again unfolded entirely, and it is a real line. And then it is folded in a particular way, which creates equivalence classes. And once again, I can say this I'm holding between my fingers an equivalence class. And over here it is an equivalence class. So everything that goes like this is an equivalence class. Same idea, but it is folding into what amounts to a segment rather than a circle. And the equivalence relation is very different if you just look at it. Where is it? Okay. Okay, so if you look at it, so 1 is aligned with, well, look at it. Okay, 1 is aligned with 12. And it is aligned with, I don't know, either that's, no, 0 is aligned with 1. And it is aligned with 23 here. You don't see the 2. 1 is aligned with 12 and 24. And the pattern is very hard to see. So the first one, 0, 1, 23, 20, 35. I'm not sure what the pattern is. There is a pattern, obviously, here because it goes back and forth in an irregular fashion, but it's not going to be as simple a relation as mod, say, 5 or 6 relation, because you don't go back for where you started like this. You go straight back and forth, back and forth. So even if you can see a pattern fairly simply here, like I said, 1, how do you get from 0 to 11? You add 11. And then you add 12. Right, to get from 11 to 23, you add 12, and then you add 13. No, hold on. That doesn't work out. I'm trying to see a pattern, and then I'm not.
I think it's just because the first one's a little bit shorter.
Oh, that's right. Yeah. So 0 to 11, add 11, right? 0, 11, then add 12. And then I still want to add 12. Now hold on a second. Even if we ignore this one, 12, and then 12 again. And on 12 again, 12 again. It keeps adding 12. Okay, so over here we're adding 12, but if we're going to here, it will be going from 12 to 24 to 36. No, that's actually 12 works out, but the trouble appears not on the one that is facing us, these, but rather if we look at these that upside down, the pattern then disappears. So as you can see, it's actually 5 is aligned with 7, and then it is aligned with 17 over here. So and then it is aligned with 29. So the point being is really not try to find a pattern here, but just to say, well, it doesn't matter what the pattern is. These are the equivalence classes. 1, 2, 3, 4. These will be the equivalence classes. And so depending on how you fold your real line, either you do it circularly or you fold it back and forth, It's entirely up to you. Which brings me to a special example that I especially interested in, and that is the metaphor is gluing. The metaphor for equivalence classes is gluing, often, in certain fields such as topology, and specifically meaning it is hard to understand. It is hard to understand equivalence relations sometimes because what are they? They are sets of sets. Well, by the way, this is the notation. The set of all equivalence classes of X under an equivalence relation denoted by X slash equivalence sign. So it is a set of subsets of X. So which makes it really hard if you think about it. So remember, the congruency class of an integer is infinitely many elements throughout. It is a hard way to look at these things, which is okay because it means that we are getting somewhere. We're trying to understand, say, divisibility and remainders, and then we create equivalence classes that will help us to understand that. But there is a way to visualize it, and we try every time we can. And one thing is, instead of thinking about necessarily of equivalence classes as sets, what if we collapse them to a point? What I mean is, I was doing that thing of creating a circle on and on, but imagine that instead of just putting it here, and then there are two different points, 0 and 7, okay? What if I glue them together? And then I say that's the same point. And then I keep gluing it. And so once again, so that the whole real line turns into a circle literally, okay? Literally, every point, every equivalence class will turn into a point. Okay, so a simpler idea is start with X. I don't want to go with the whole real line. It's just too much complication. I'll take a simple example. X is equal to 0, 1. Okay, equivalence relation rather. Well, X is equivalent to X. I don't have to say that, but sometimes it's just a good idea to repeat it. And then 0 is equivalent to 1. Okay. This is the description of my equivalence relation. Once again, X is equivalent to X, always. It's a reflexivity axiom, so we don't have to repeat it, but early on we will. And then I add one non-trivial part to this relation, and that is I declare 0 equivalent to 1. Okay, so things are really not complicated, but there's a very simple equivalence relation. Like I said, there is one equivalence class for each point, except with exception of 0, 1 that turns out to be equivalent to each other. Okay, but now what I could do is to visualize the equivalence relation, not rather equivalence relation, but rather this is X. How do I visualize the set of equivalence classes? And like I said, there is only one equivalence class inside of the interval 0, 1. So X, the equivalence class of X is equal to X, remember this, when X lies between 0 and 1, right? Okay, and the equivalence of 0 is equal to the equivalence class of 1, okay? So two different points, the ones inside and the two endpoints, and then that's the two different, well, I'm sorry, would be a complete way to put it. So if you lie between 0 and 1 inside of the interval, then you have only every equivalence class is very simple, just one point, okay? But the two endpoints combine together in 1, okay? That's what the second line says. So the equivalence class of 0 and of 1 consists of 2.01, okay? So, but now what if, based on this information, I try to visualize the equivalence classes, each of which would be considered a point? What do? I simply glue 0 to 1. to make that equivalence class into one point. So make this into a single point. So if you want a metaphor for that, that's a gluing. So when you glue things, or think stronger words beyond gluing, welding.
Hammer, nail, nail them together.
Yeah, not a hammer, what's called
Staple them together.
staples, all good, all good. Yeah.
Industrial staples.
Staples, welding, soldering, all of those.
Sew them together.
Right, exactly. So that way they're two almost literally two pieces of fabric, and then they become one. If you do a good job, there's no gap, there's no visible, and then it's like fabric becomes one. Okay, so that is the visualization idea, and then you realize what my class or set of equivalence class it turns into. It turns into glue or solder 0 to 1. This is 0, this to 1, become 1 point. A circle, right? So this is 0 equal to 1. So they were, by idea, they were equivalent, but then we make them equal. A single point. Okay? And that way you can build a lot of things. So making a circle from a neutral is a big deal to begin with, because that is creates a hole. So there was no hole, and then all you did just one single point, and then you have something which has a non-trivial topology. It has a hole in it. Okay, so similarly, how do you make a sphere? How do you make a sphere in following this idea? No, I want to have an equivalence relation. So this is example 1, how you make a circle from a segment. If now my interest is to make a sphere, how do I make it? What should I make it of? From? You don't. You got to have a set X first. What is the set X?
0 to 1. 0, 0, 1.
Okay. Well, good question. Can you make a sphere from a segment?
If you rotate it.
Well, no, you don't allow it to rotate. You got to build it by gluing. So this is my interval. It's a little bit longish, but how do I make a? I can make a circle. How do I make a sphere? The problem with it, look at it. You can't. It's thin. It has no width for me to make it. Unless you try to do it like this, it becomes. Yeah. Well, no, that was your answer. I think that was your answer. You want a segment. The idea is, okay. Let me help you out. A circle, a disk. So X is a disk. That's my set. What should be my equivalence relation to produce somehow the sphere?
The diameter.
Do what? Diameter? What do you, diameter? You mean this?
Yeah.
What do you do with it?
You make it a set.
It is a set. Now, what is an equivalence relation? Remember, equivalence relations are pairwise identifications. So you got to say which points, just like I did in the previous example. I say which ones are equivalent, and then if they are, I glue them together. So there are only 2 points to glue in the previous example. Now, any thoughts of how you make it?
You get from 0 to whatever the biggest section is.
From 0
to whatever the widest diameter is.
The diameter goes through the center. You realize that? Yeah. So what do we do with it?
So you're looking for the end points, or you're looking for the middle?
I want to say that these points on the disk, what I'm talking about is literally a circle. There's no hole in it. Okay. And I want to think about. Well, let's make it literally. This is just not. This is too abstract. think about a piece of fabric, and you want to make, what do you want to make? It's a bag. Okay, how do you make a bag from a piece of paper? Yeah. Okay, close. Okay, so keep going. So if you,
I don't know, you just like sew it together.
okay, well, did you see what you just built? Well, let's take a look at what he just built. What did he just
It's a
build?
duffel bag.
That's not how you make a bag.
No, but he built something interesting. What do you call it?
Cylinder?
It's a cylinder. He built a cylinder from a piece of paper. Okay, so well that is seemed to be a simpler idea. So let's explore it. X is a square, and then we could build a cylinder. So that's not just for fun. I want to know what the equivalence relation is. You did it, so you can tell me what the equivalence relation is.
I get one.
Would it be like the side is equivalent to the circumference?
The surface area.
No, the surface remains, the surface, nothing happens to the surface. You only glue the edge, one edge, in fact, the two edges. Two edges, take them and glue them together like this.
So the
Right?
side-
He did that. So just, now that you have to make it more mathematical.
The side link's equivalent to the circumference, and then the side.
No, you got to do it point by point. So this is how it's done. One point, these two are glued together. And then these two glued together. You see it? And then we have more points. These glued together. And then those glued together. Okay? Looks reasonable?
So you just,
Yeah, they did that, right?
Yeah, he did
So it is the plan of how to do it. Take every green point and glue it to another green point, the other green point. The blue points also glue together, right?
That. I'm not good at art.
It's this is mathematics.
you can like find
I don't have a piece of paper.
Do you want this piece of paper?
Yes, please. Could you pass it to me? So it's a good example. I thought it's easy to make a sphere, but maybe
Just keep it.
no. So okay, so I don't have way to color it, but you can see how. Suppose this is my piece of paper. These two are green, and then bring them together like this. Okay, that just one point. That's not enough. It does not create a cylinder. That creates. Look at it. It doesn't create much. Okay, but once I starting putting more points here, so say then I take blue points too. So then we have more and more points glued together, and then at the end of this process, I have all the points along the edge glued together pairwise. Okay, which creates a cylinder. Okay, now it can be turned into something more mathematical if you're willing to, just the way I did it over here, if you're willing to put a coordinate system on it. So let me do that. So I put a coordinate system, x, y, x is here. I put a 1 and 1 and 0. So it is a 1 by 1 square. Okay, so here how it works out. 1, 0, 1, I'm going green. 0, 1 is equivalent to what? What's the other green? 1, 1. Okay, and then say in the middle, the orange one. The orange one is 0.5, and it is equivalent to,
1.5.
no, 1.5, okay? And then at the bottom, the red one is 0, 0 is equivalent to 1, 0. Okay, you see a pattern now? Okay, so yeah, I can write it in one line. So what's the if I combine the two together in one, what do I get? The first, the two edges of the piece of paper. Not we ignore these for now, and we glue them together. So this one is coordinate is 0, and the second coordinate, how about 1? It's equivalent to what?
1x.
1, 1. Okay, so for each y on the for each y there will be a point on the edge, and there will be a point on the other edge, and they're said to be equivalent to each other, and you glue them together into into what amounts to a cylinder. Okay? So, all right, so it's compared to what I had over there, it is with a way simpler example. When I started with the edge, 0 is equivalent to 1. That's very easy to say right here. Okay, and when you have a surface, it's more complicated, and you have to have 2 coordinates. Okay, what if I identify the opposite? So this is my square or rectangle. I identify these, and I produce a circle, a cylinder. What if I identify these two? What? Another cylinder, right? So that doesn't make any difference. Okay, what if I do both?
Then you're just gonna have like a.
What?
Plane?
No. So this I start with this, okay, and then I have to. These edges are also identified.
So you have to put
Like a
them
3D
Yes.
circle donut?
No, donut. It is a donut.
like a tie.
What? What's the word? The word is the torus. The torus. It's like empty donut. So it's only surface. There is nothing inside. But like I said, you start with a cylinder, first identification. Then you have to identify these two, and then you turn it into, into this. Oops. Okay. So I identify, to get this, I still start with this square, okay, and then I identify 0y with 1y, as we already did, and then I identify the opposite edges vertically. So I'll have x0 identified with x1. Okay, so this one is I identify the vertical edges, and then over here I identify the horizontal edges. The end result is this torus. Okay, so you can actually see, like with the cylinder, if I can point out where the gluing part is. So for example, this is the gluing part of the cylinder, and then it is, with respect to the torus, it's here. It's like the, what do you call it? The equator. Okay, so that's the first edge glued together. What about the green one? What about the blue one?
The inner equator?
What?
The inner
No.
equator?
It goes this way. That's right. Yeah. So like this. The torus. Okay. So you can build very interesting things from a piece of paper, and that's what topology does. Okay. So that we might have time to take another look at it. But what about that example I started with? The second example of the how do you build a sphere? What?
Just national.
Oh, can you be more specific? Well, as a hint, how about we do not do anything with what's inside, and only we deal with the
So you want a hollow sphere?
yes, hollow, definitely. You cannot make something that's not hollow from a piece of paper. You can make it small. You can not expand it. You know. So what do I do? A circle. Suppose so. Your piece of paper this time is not a square. It is a circle. Well, let me try to do my best here.
You just take the points on the opposite sides of each other and,
And-
fold them together like that?
Pick-
Like
pick-
the needle?
Oh, that's a good question. No, but what you're building is really very interesting. It is a very interesting object that you're going to build.
Yeah, I wrote everything but a sphere, I guess. Versus a cylinder.
Okay, it's ugly, but so what you're suggesting is that what he actually said, suggesting identifying pairwise like these points, and then these 2 points are also identified. These two.
Like a ring.
What they're going to turn into is to be discussed in different circumstances. But it is a much simpler than that. You don't do pairwise like this. You do all points together, like this. You're you're holding a bag like this. Okay, so you start with this. This is just too small, but no, you have to. No, I cannot. So a bag, go backwards. Imagine that you have a bag, and then how do you flatten it? It's really not, you're holding a bag like this. How do you flatten it? You flatten it like this. Okay, and now reverse. You take all the edges, the whole edge, you take the whole edge, which is a circular, and bring it together in one point. Okay, so in other words, let me point it out. It's actually fairly straightforward. What I'm plotting here, what is red? It is one single equivalence class. Okay, so the edge becomes one single equivalence class. So all the points on the edge are equivalent. And so under the gluing metaphor, that equivalence class, the edge becomes one single point, like here. Okay, does it help? Right, so like I said, identify, it's certainly not about anything being flat, and you cannot make literally a sphere from a flat piece of paper. That, remember, mapping problem, you cannot make maps perfectly fit the surface of the Earth because it's curved. So we cannot do this. With cylinder still works out because cylinder is, appearances contrary to, but it is actually flat. But both the sphere and the torus are curved. They have curvature, and they cannot be made of anything flat, unfortunately. So that's why you have to tear them, and you got to think in terms of kind of more abstract sense than this, than just a piece of paper. Better if it is think about a piece of rubber, maybe might help a little bit.
How do you get all that distance in one point?
What do you mean how? You just
No matter how many points you match
Yeah.
up, there's always going to be like some of them that aren't going to want to.
I'll keep going. Yeah, you better imagine that you do it at once, like this. Yeah, imagine, like it's like a hunting thing, trap. Imagine like a net lying on the ground. You step on it and it does this. You seen it? But in the movies, obviously. So it's a trap for animals. So you trigger you maybe trigger some mechanism, and there's a weight, and it brings the whole net up, and at the same time closes the bag, and you are inside of the net.
And that's a sphere.
You can say it's not exactly sphere, but we don't care. That's topology. We don't care about the shape, but only of whether or not there's a hole inside or not. Okay. So so that is certainly deserves. You can talk forever about this, but there is one more example. I don't think I want to go on. Just jump to the next topic yet. So I'll mention something that is a more challenging and way less visual example of an equivalence class. And that is, I brought it up some time ago, and that is the equivalences under bijections. So bijection, a function f from x to y is called a bijection. Well, remember what it's called a bijection? One-to-one onto. Okay, so you don't only have to use the word bijection. It's a luxury, frankly. So if you just understand what a one-to-one and onto means, then you're fine. So what do they mean? One-to-one onto? No, Rick.
F of x equals y, or like x is y, and just like a straight line, like 1, 1, 2, 2, 3, 4, 4.
Yeah, something like that. Can you make it more specific?
For every x value, there's only one y value, and for every y value, there's only one x value.
Right. Well, the first part, you don't need the first part because every function satisfies that. For every x, there's only one y. That is simply the definition of function. But the other one, for every y, there is 1 and only 1, 1x. So y is equal to f of x. So you can find, for every y, you can find x backwards. Going backwards. Forward, this always works out. That's your function. It's defined for every x. Okay, but backwards it doesn't always work out. The counterexamples are naturally x squared, which for every y there are 2, right? For every y there are 2 x's on one hand, and some x's and some y's, which makes it not one-to-one. So this picture that I pointed out here indicates that y equal x squared is not one-to-one. But it's also not onto because there are values of y, such as this one. No x, so y equal x squared is not onto. So if you think about this function as a function from R to R, as we frequently do, then this function is neither one-to-one nor onto. So onto means that the range is all values. So y, it has to be covered on one. That's the existence part. Okay? And then, but then when you go backwards, you can go backwards according to onto part, but then turns out that you can go back in only one way. That's the uniqueness part. So there is an x, and there's only one such x for every y. So we're going backwards from y to x, and there are, if I pick y equal 1, then there are 2 x's, negative 1 and 1. That's not good. And then there are, if I start with negative 1, there is no x. So it's neither no one-to-one nor onto. Okay, so big one in mathematics. This kind of the next step in studying set theory is not intersections, unions anymore, but rather this kind of things, functions between sets. And then when the sets have no algebra, those are not numbers or even vectors. So what is that to look at? And there is plenty to look at. And this is one thing is in set theory there is not much else to do unless you look at this. Is it one-to-one and onto? And so that definition certainly needs to be known. Okay, so we'll just have to do some more of this next time.